So a couple lessons back, we saw conservation of mass in integral form. We're actually going to use some of those concepts to derive conservation of mass in differential form now. So to do that, we're going to consider a infinitesimal cube. It's not necessarily a cube because dx, dy, and dz are not necessarily the same length, but cube's the easiest way to call it. And so I have some cube of fluid, that's my control volume. In the middle of that cube, there's some density rho, and that fluid is moving with some velocity v, which has vx as an x component, vy as a y component, and vz as a z component. So as I mentioned, we're going to use the conservation of mass equation in integral form. So on my control volume, this blue box, I have dy dt integral over my control volume, rho dv, plus integral over the control surface of rho v dotted with dA. Now what I need to do is evaluate all these terms. So I want to figure out what this is in terms of my box, figure out what that is in terms of my box. So starting with the easy term, the dy dt over my control volume of rho dv. My control volume is not changing. I have dx, dy, dz as my dv. None of that changes in time. The only thing that does change in time is rho. So when I do this derivative, all I have is partial derivative of rho with respect to time times my control volume dx, dy, dz. So that's my easy one. Next thing I want to do is the second one. So the second term involves integral over control surface. This guy is going to have all these contributions from velocity coming in and out of all six sides. So you can do that on one side basis. So we'll see that next. So doing this for just one side, in this case I picked the right hand side, so this side over here. I want to evaluate basically this integral, rho v dotted with dA for that one side. And so what we have to do is figure out the value of rho and v on that side with the Taylor series. So rho on the right hand side, again Taylor series from the value that I know in the center. So from the center, I take the derivative in the direction I'm going, d rho dx, the distance that I'm going, dx over 2, and this is 1 over 1 factorial in the Taylor series. Then the next term, 1 over 2 factorial, second derivative, dx over 2 squared, and so on and so on. So that's the expression for my density on the right hand side. I can do the same thing with my velocity on the right hand side. Just velocity would be velocity in the middle, dv dx, d squared v dx squared, and so on. And the velocity that I want in this rho v dotted with dA is the perpendicular velocity. So in this case I want the x velocity. So this expression, I get my rho expression from up there. I cut it off here because I'm assuming that dx is small. So dx squared is a really small term, so I'm ignoring everything past that essentially. So that's my Taylor series expansion of rho. Similar Taylor series expansion of v. And then I need my dA. And so if I'm going in the x direction, the area is this face here, which is dy dz. So my area dy dz. So that is that expression there. And then I can basically expand this out, FOIL it if you will. I get rho and v. I get this term times v. I get that guy times that guy. Gives me that. And then technically I have the last terms as well, but the last term again is going to be dx squared. So dx squared, I'm assuming again it's small, so everything beyond that are going to be small terms that I'm going to ignore, and then I still have my area at the end of that. So that's the right hand side. What I want to do is do a similar thing for all 5 other sides. So the next side to do is the left side, and so there's a few little differences here than the right hand side. The first thing is that when I did all my velocities, Vx, Vy, and Vz, I'm assuming they're all positive. In other words, I'm assuming Vx goes to the right, I'm assuming Vy goes up, Vz comes out of the board. And so when I did the last one, Vx was coming out of my control volume, coming out is a positive number. Here I have Vx going into my control volume, so going into my control volume, I need a minus sign, so that's issue number 1. Then the second thing, when I did the Taylor series, from the center, I'm going to the left. In other words, I'm going in the negative dx over 2 direction. So I just put that negative up front. So it's rho minus d rho dx dx over 2, and so on. Similarly for this guy, it's to the left, so the minus sign comes out. Again, span that out, I get this expression here, which is very similar to the one on the right-hand side. Difference is that this guy's negative, whereas he was positive in the other one. It's then very similar procedure on all the other four faces. So on the top, I have rho Vy going in the y direction now. That's what I care about. Again, my Taylor series is in the y direction, so I have d rho dy and dy over 2, and reduces down to this form. Area in this case is dx dz. Similarly for the bottom, pretty much the same thing, but I have this minus sign for the same reasons as I had the minus sign on the left-hand side. And the same thing for front and back. Now dealing with z velocities and dz over 2s. So now what I want to do is, I have all 6 sides. I want to add them all together. So when I add them all together, we can see that the pairs, in other words the front and the back, first two terms are going to cancel. So I have rho vz minus rho vz. And then the next two terms are going to add together. So essentially I have vz d rho dz, dz over 2. I have another one of those, so essentially the 2 is going to go away. Same thing here, I'm going to have the 2 go away and end up with those two terms. So I'll have those two terms from front and back, those two terms from top and bottom, and then these two terms from the left and right without the 2's. So adding all 6 sides together gives me the expression for this second term in my conservation of mass equation, the integral over the control surface. So from the right-hand side, I have vx, d rho dx, dx dy dz, plus rho dvx dx, dx dy dz. That's from right and left, I mean. And top and bottom gives me vy, d rho dy, dx dy dz, rho dv dy, dx dy dz. Then top, front and back gives me the same thing with z's. So I can see that what I have is this first term, v and rho with an x derivative. That's basically the product rule, using both rho and v as functions of x. So I can make that into a single derivative of rho times vx. Similarly for the second line, y derivative of rho times vy. Third line, z derivative of rho times vz, and everything is multiplied by dx dy dz. And then what I can realize is that my x derivative goes with my x velocity, y derivative with y velocity, z derivative with z velocity. So an easier way to write that is the divergence of rho times velocity, and of course dx dy dz at the end. So putting everything together into conservation of mass integral form, I had this dy dt integral over the control volume plus this integral over the control surface. We found that the integral over the control volume was d rho dt dx dy dz. Just found that the second integral was the divergence of rho times velocity dx dy dz. Basically divide by dx dy dz. I'm left with d rho dt plus the divergence of rho times velocity equals 0, and that is the conservation of mass equation in differential form, also called the continuity equation. So that last equation was the general form of conservation of mass in differential form. Works for any scenario. There's a few scenarios where it becomes simpler. For example, steady flow. Steady flow, there's no time dependence, so that first term, d rho dt, goes away. All we're left with is the divergence of rho times v equals 0. Another special case is incompressible flow. For incompressible flow, the density doesn't change with time or space, so the d by dt term goes away because again density is not changing. Then I'm left with this term here, but then I can pull the density out because it's constant, it's not changing. And then when I pull it out, I can divide by it, and I'm just left with divergence of velocity equals 0. So if I have an incompressible fluid, the divergence of velocity has to be 0 for conservation of mass, and of course divergence of velocity dvx dx plus dvy dy dvz dz equals 0. Now the way I derived the conservation of mass equation, this guy here, was using x, y, and z coordinates. Sometimes I might want to use different coordinate systems, cylindrical, spherical, whatever it is. And so what I could do is go through that whole procedure again, but instead of using a cube, use a sort of wedge shape object for cylindrical coordinates. But the good news is I don't have to, because I'm going to end up with the same equation even if I do that. So I still have this equation no matter what the coordinate system is. The only slight complication is that this divergence gets kind of funny in other coordinate systems. In x, y, and z is simply derivative of x plus derivative of y plus derivative of z. In cylindrical coordinates, for example, what I end up with is actually 1 over r derivative, r times vr, 1 over r theta derivative, and then my d by dz stays the same. So as long as you use the right version of divergence, you still use this equation no matter what the coordinate system is. So I'm going to finish off today's lesson with a short example. I have a two-dimensional flow in the xy plane. X component of velocity vx is a times x, a is a constant. I want to determine a possible y component of the flow, and then also figure out how many possibilities are there. So I want to come up with one possibility, then I want to know how many other choices do I have. So solution to this guy, he's incompressible. So if I have an incompressible flow to satisfy conservation of mass, I need to have the divergence of velocity be 0. Because this is a two-dimensional flow, xy plane, dvx dx plus dvy dy, there's no z component, so all I have is these two terms, equals 0. And then I know that my dx is a times x, a is a constant, so the x derivative of ax plus dv dy is 0. This derivative is just a, because a is a constant, plus dv dy is 0. So rearranging that, I know that dvy dy has to be negative a. So now we just integrate that, I get that vy is negative a times y, and that is one possible velocity component in the y direction for this to be incompressible. Now to answer the second question of how many possibilities are there, when I did this integration, I left something out, namely the constant of integration. It's not really a constant because this isn't a full derivative, this is a partial derivative, which means that when I integrate, I don't necessarily just get a constant. I could have a function of x, because when I have a function of x, with a y derivative goes away. So what I really should have is my original answer of vy is negative a times y, then plus this arbitrary function of possibly x and or t, because any one of those variables will go away when I take a y derivative. It's a 2D flow, so I didn't include z, but basically my arbitrary constant function should be anything that I'm not taking the derivative with respect to. So that's my full answer, and I can see from this arbitrary function be whatever I want it to be. So infinite solutions, infinite possibilities.